Hello there and welcome to today's webinar, sponsored by Sensonor, inside GNSS and inside Unmanned Systems, and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they explain how an inertial measurement unit assembles and delivers precise timing information, typically at a much higher rate than the co-integrated GNSS receiver. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Expert panel session with all three of our panelists. Now, we've invited you, along with over 300 professionals from 37 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher inside GNSS and inside Unmanned Systems, would like to take a moment to welcome you and introduce our sponsor and our main moderator for today. So over to you, Richard.
Thanks so much, Lori. On behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, Sensonor, I extend a warm welcome to our audience from around the world for today's webinar. We really value your participation, and we're delighted you're with us today. I'd like to introduce Hans Richard Peterson for some opening remarks. Mr. Peterson has more than 21 years of international business and technical experience, and he's in charge of product development and global marketing at Sensonor. Hello, Hans Richard. Welcome.
Yeah, hi, Richard. Thank you for that. So at Sensonor, we have worked with Inside GNSS for more than 10 years and have enjoyed their focused work in the position and navigation and GNSS community. So during the last decade, we have engaged a range of customers and applications in commercial, military, and lately the space segment. When planning this webinar, we searched to find a topic that would be of interest to many of our customers, but that had not been discussed at great length in the past. We had to address something different than stability and angular random walk that is too often being talked about, however, that are also important to Gyro and IMU integrations. So recognizing that some of our most challenging discussions with customers have been on the details of timing, we thought that this would be a valuable topic to dive into since it hasn't been talked about that much before. Also understanding that this would be or addressing a somewhat narrower audience. So I really look forward to get into this topic today, and we have also gotten some really good speakers with us for today's session. Back to you, Richard.
Thank you, Hans Richard. Appreciate that. So now I'd like to introduce our moderator for today's webinar. Alan Cameron is the editor-in-chief of Inside GNSS Magazine and the PNT editor for Inside Unmanned Systems Magazine. He's covered GNSS, PNT, and autonomous industries for more than 22 years, focusing on technical issues around continuous, reliable positioning, navigation, and timing. Alan, the floor is yours.
Thank you, Richard. And thanks to everyone who's tuning in from around the world. I'm glad to see that once again we have a truly international audience. The topic, as Hans Richard said, is a little bit different. It's new. It's something that, well, it's not new. Let me take that back. It's new to me. I learned quite a lot in the run-up to this webinar, hearing from our panelists about an aspect of inertial measurement that I was not very familiar with. Of course, I knew about time tagging, but I didn't have a real good understanding of what it was, and I've gained that in our practice sessions. So I look forward to sharing that information with you. I look forward to our panelists, let me correct that, sharing that information with you. And we have an all-star panel for you today. Dr. John Raquette, you see his photo there, formerly the Air Force Institute of Technology, now with Integrated Solutions for Systems. Reidar Holm from Sensonor, and Bjorn Scott from Electronics. Dr. Raquette will explain the concepts, the various concepts of timing in inertial technology. Raidar will show you how it's done at Sensonor, the inner workings of an inertial measurement unit and the various timing aspects that it can supply. And Bjorn will show us a fascinating application of it in the railway sector, ensuring that trains function safely because of a little known or little understood factor, just how smooth and straight and precise the placement of the rails are. We'll get into all that and more with your questions. Before we launch into it, Lori, let's learn a little bit about the audience.
Yes, let's do that. Coming up on the screen is the first poll for today, and we'd like to hear from each of you. What level of synchronization does your application or product require? Seconds, milliseconds, microseconds, nanoseconds, or perhaps not important? All right, looks like 3% saying seconds, 33% milliseconds, 38% microseconds, 23% nanoseconds, and 4% coming in with not important. So any thoughts here, Alan?
Well, I'm glad to see that by far the majority, well over 9/10 of the audience, does have a need for precise timing at various levels, and fairly evenly split there. I think all sectors will learn something from this webinar. But of particular interest, of course, is going to be the millisecond, microsecond, and wow, getting into nanosecond synchronization among sensors is really getting into high precision. Well, let's get underway. We're going to hear first from Dr. John Raquette, Vice President for Dayton Operations at Integrated Solutions for Systems, or IS4S, where he develops efficient, pluggable approaches to all-source navigation. He founded and was formerly the director of the Autonomy and Navigation Technology Center at the Air Force Institute of Technology. He has a multidisciplinary background in electrical engineering with a PhD in geomatics engineering from the University of Calgary, a master's in aero-astro engineering from the Massachusetts Institute of Technology, and a bachelor's degree in astronautical engineering from the U.S. Air Force Academy. He's a past president of the Institute of Navigation, has been a U.S. Fulbright Scholar, and is an ION Fellow. He's been developing navigation system technology for more than 30 years. Dr. Raquette, it's a pleasure to have you. Please proceed.
All right, well, thank you, Alan. As we begin, many of you probably have used an inertial system, and there's a lot of practical issues to consider. One, of course, is performance, all the things that we're used to thinking about, the quality of the sensors themselves. Of course, any practical system, you have to consider size, weight, power, and cost. But what we're here today to talk about is timing. And this turns out to sometimes be one of the most important things. In fact, I kind of say it's like our heart. This is very important, but commonly overlooked. Most of us don't think about our heart beating as it beats second by second. So let's look here. Use this example as kind of a typical integrated system where we have a number of different sensors, including an IMU, and those sensors, the data from them is collected and brought together into an integrated navigation system, and that's going to have a couple of different functions there. The first is what I call I/O and timing, and this is essentially where it's collecting the data, time tagging it, and sort of preparing it for use in the sensor fusion software, which then generates an output. Now, two things have to be true by the time it gets to that sensor fusion software. First of all, of course, all the data needs to be present there, needs to be collected in one place. But most important for today is that the relative measurement times of validity need to be known between all of the sensors. And I'll explain what I mean by that in just a second. So measurement time of validity, let's kind of look at what happens between when something is sensed and as it goes through the system. So we're going to call time zero the time at which the sensor actually physically sensed the measurement. In the case of the IMU, it would be the rotations or the specific forces or accelerations. That's when it was actually sent, but then it appears on the wire at some time after that. And between when it was sensed and the wire, there's signal processing, there's maybe forming the message itself, output buffering, those kinds of things. Okay, then later on, it is recognized by the system. We'll call that time T2. And between time T1 and T2, you might have input buffering. You might be parsing a message to find out, okay, here's the message. Now I know what that is, those kinds of things. Then there is T3. This is the point at which the sensor fusion software actually starts using that measurement. It may be waiting for other measurements. It may be waiting for CPU processing time. Here's where, if you're using a Kalman filter, the filter starts operating on that measurement. And then finally, we get to time T4, which is where the output is generated. And you can see there's all kinds of different times here. But when we're talking about time of validity, what we mean is really this T0 time, the time at which this event actually occurred that the measurement is expressing. Now, let's not confuse time of validity and latency. Time of validity, like we said, is when the measurement actually happened. And as you'll see in the next presentation, that there's potentially, that's maybe, there's complications even with that. There can be signal processing, and so the measurement that's generated may not be all just from one instant. But nonetheless, we're going to say, when did that measurement occur? That's the time of validity. The latency is how long it takes us to see that measurement. And we can define latency differently. We could define it as T1 minus T0, or really any of these other times minus T0. But latency is really only a concern for real-time systems. Okay, so this relative measurement time of validity, when we get to the sensor fusion software, at that point, we really need to know where all these sensor measurements, their times of validity, are relative to each other. And in a sense, they really need to be all expressed relative to the same clock. There's two ways to do that. We can either require every sensor to independently synchronize to something external, like maybe GPS or UTC. But probably more commonly, we relate them all to some kind of a common clock in our integrated navigation system. So let's kind of focus in on IMU measurement timing. This would be true of the other sensors, but particularly let's think about the IMU today. So we have now an IMU over here. It has an IMU clock, and we have a navigation system which has its own clock, and the measurements, of course, are coming across, and we have our time T0, T1, and T2. Fundamentally, what we're going to need is we're going to need to know what is that time of validity relative to what the reference clock is saying. So what's the reference clock time of that time of validity? We could call that T0 ref. I'm just going to call that the time tag, just to not be being overly technical. So the time tag is the measurement time of validity expressed in our common reference clock. So what does it represent? Well, here are perhaps a sequence of IMU times of validity for data coming out of an IMU. There's a couple different kinds of IMUs. Some IMUs output what we would call sampled measurements. These, for the accelerometer, these would be the actual specific forces that are sampled. The units would be meters per second squared. For the gyro, these would be actual rates in degrees per second or radians per second. And this is probably what you conceptually think of by accelerometer and gyro outputs. However, there are other IMUs that output what we would call integrated measurements. In other words, these are outputting delta V's and delta thetas, where delta V is really the integrated specific force since the previous measurement. Same thing with the gyro. The delta thetas are the integrated rates since the last measurement. So the units in these are in meters per second and degrees or radians. So it's important to understand, time of validity kind of means something a little bit different with those two different types of sensors. So then we have to ask, well, how accurate do we need to know our time tags, our T0 ref? And of course, it depends on what we are doing. Let's use a couple examples here. First, we have a case of GPS position aiding of an inertial. Very, very common use case. So the key question we have to ask is, how much does this GPS measurement change over time? as we're relating it to the inertial measurements, because somewhere in that estimator, the IMU measurements are going to be compared to the GPS measurements. And if the time tags aren't correct, then this comparison is going to have a time tag induced error that's sort of related to how much they're changing. Well, change in position over time is velocity. So in this case, the time tag error is really the velocity time, the time tag induced position error is the velocity times the time tag error. So velocity is really the driving factor. So as an example, let's take a system where we have a 0.1 second time tag error in our inertial system. Does that hurt us? Well, if we're doing a pedestrian example, where maybe our max speed is 2 meters per second, then our time tag error might be 0.2 meters. That may or may not be an issue. That may be just fine. If we're in an auto application where maybe the max speed or max velocity is 35 meters per second, now we're going to end up with potentially a 3.5 meter time tag induced position error. That's starting to maybe be more painful, but again, that depends on our application. If we're in an airliner and we have that same 1/10 of a second error, now we have a 30 meter time tag induced position error, and that may be getting more and more painful. So you can see it's not just what is the error, but it's very much what is the application and the use. And that's for a 0.1 second error. Now let's look at a little bit more challenging case for timing. In this case, we're going to look at an IMU integrated with a camera. And for this particular integration, what we're going to be doing is we're going to be identifying features in the images from the camera and then relating those features to what the IMU is saying. So we're essentially kind of tracking the features and relating them to the inertial. So now our question is, how does the feature or the image features change over time? In GPS, it was how does the position change? Now we're tracking the features. That really comes down to asking, well, what's the change in attitude? And that's really a rotation rate question. So rotation rate is now going to be our driving error. So let's assume we're using an HD video stream, a 45-degree field of view. We can resolve features within a pixel, and if you work that out, that means each pixel represents 0.04 degrees. So if we want to track a feature, we need to make sure we don't have any more than 0.04 degrees of error due to timing. So if we do like many people do when they start doing image-based navigation, we put a system on a cart in an office hallway. You know, for this setup, you can't move the cart that quickly. Maybe there's a max rotation of 10 degrees per second. So if I look at my time tag requirement, I need to make sure I have no more than 0.04 degrees, and I work out the math on that. That means I have a time tag requirement of 4 milliseconds or better, right? So this is a much more stringent requirement than we had with GPS. And that's for an office cart in a hallway. If we're actually on a car driving down the road, where maybe we're going to see 300 degree per second bumps, you know, where the pothole or something, and you get a fairly rapid rotation. Now you can see our time tag requirement gets down, you know, 1/10 of a millisecond or so. So much, much more stringent. So in terms of the accuracy that you need, it certainly does vary by sensor and application. And the really key thing to consider in any particular application is how much does the sensor that you're relating to the IMU vary over time. And then we have to compare that to the desired accuracy. And ultimately, it's going to depend on which sensors are being integrated, the operating environment, and what overall desired solution accuracy that you need. This approach can be applied to really any kind of sensor that you're integrating with an inertial. So now we're going to transition and talk about, well, how is it that we do this time tagging in practical systems? And it turns out there's many ways to do it, and they all involve trade-offs. Some are easier, some are more accurate, some put requirements on the sensor, some put requirements on the integrated navigation system. And I'm going to quickly go through really I'd almost call them families of ways that you can do this. This is not super detailed, but just giving the top level approaches where we can get that IMU time of validity expressed in our reference clock time. So the first one is very simple. It is to measure this when the measurement comes into the system and the software recognizes it, to just time tag it then and say, there we are, that's the time of validity. This is the most common thing that's done because it's very easy. However, there's a latency involved. It's the T2 minus T0 latency. So whatever time it took for it to get through the network stacks and everything else, that's going to be present. And that latency is sometimes somewhat variable because some of the software-oriented things are not super regular. So this is the least precise approach that can be taken. Now, we could use time of arrival, but what I would call a hardware-based approach. And in this, we might be using some sort of hardware like a FPGA to measure when did that data bit arrive at my system according to my reference clock. And that could be measured very precisely. So this gets us to where really we're measuring T1 minus T0 very well. We still have that latency, but this does require pretty complicated hardware interaction with the measurement stream in a way that often isn't existing in systems. So timing pulses can be used, and they can be sent from the IMU or to the IMU. So this is a way that the IMU can send a timing pulse, and this would be a case where it would represent, or it would send a pulse at the instant that the measurement is actually taken, at the instant that it's valid. And so this pulse might be coming out at the rate of the measurements, 200 hertz, 300 hertz, 100 hertz, whatever the rate of that IMU is. Or it might be some every so often, every 200 samples it would give it a pulse. But the point is it's telling you when the time of validity is. So this would enable very, very accurate time tags, but it's going to require that integrated navigation system to have hardware to measure that pulse and get a precise time tag of when that appeared relative to what its reference clock says. Now you could also allow the IMU to just provide a pulse which represents the IMU clock, like a pulse per second, with a message that says my IMU clock was at this time at the last pulse you saw. And what that allows the system to do, again, if they can measure the arrival time of that pulse, is to get a good understanding of the difference between the reference clock and the IMU clock. And then the measurements that come time tagged with the IMU clock, those can just be related to the reference clock. Again, this allows very accurate time tags, but it still requires hardware in that system to be able to time tag that pulse that comes in. Now we can send pulses to the IMU, right? And here's an approach where the reference clock sends a pulse when it wants the IMU to take a measurement. So that by definition means I know when that measurement is valid. But this requires a pretty complex interaction between the two systems. And there still is a need to know precisely when that pulse was sent in order to be able to understand what the time of validity was. So the idea is the system sends a pulse, says take a measurement now, the measurement comes out, I can time tag when that measurement occurred based on when I sent that pulse. In a similar way, we can send a pulse, and this is pretty commonly done in IMU systems. So send a pulse, and the IMU system can detect when it saw that pulse and send out a message that said, according to my IMU clock, I saw a pulse at this particular time. So then that integrated navigation system can look at that data stream, and that allows it to relate its reference clock time when it knew it sent the pulse to the IMU clock time when it received that pulse. And that allows, again, for very accurate time tagging. It still is going to require hardware on the integrated navigation system side to know when it sent that pulse. So another way this can be done is through timing approaches such as network time protocol or precision time protocol, PTP. These are, if you have like an Ethernet or even a USB, these allow, for example, the IMU clock to be synchronized to the reference clock just by following the protocol. So this is very convenient because then you can just send the messages over with the IMU clock timestamps, but those will be sort of the same as the reference clock because the clocks are synchronized. This does enable precise time tagging without requiring sort of the hardware to do pulses. And really there's only just one interface. But the IMU needs to support NTP or PTP. And it does require a two-way data bus like Ethernet or USB. And if you're using PTP, then there's specific hardware requirements according to the IEEE protocol. Note that the accuracies of NTP and PTP are different. NTP is sort of a 0.2 to 1 millisecond accuracy. PTP can be 0.2 to 1 microsecond accuracy. The final approach is what is sometimes used in systems as well, which is where you have the IMU, perhaps it has direct access to a GPS signal, so it can time tag its measurements with absolute GPS or UTC time. The integrated navigation system can do that, and then the measurements are all really one time scale. So again, this can be pretty high precision, but it's going to require this absolute time to be accessible to every component of the system. So that's feasible in some cases it's not. So in summary, we always need to think about time tagging when we are going to integrate IMUs with other sensors. And it's an often overlooked thing, but it tends to be very important. The accuracy of that time tagging will very much depend on what we're integrating, the operating environment, what kind of accuracy we need in the final solution. And there can sometimes be very, very stringent timing requirements. And there really are a plethora of ways that we can generate time tags of IMU measurements. And it depends really on your own application and the trade-offs involved with that to determine which one might be feasible for you. Thanks. Back to you, Alan.
Thanks very much, John. And for those of you in the audience, if you have questions about the presentation you just saw, you're encouraged to put them through the question panel, and we'll get to some of them in a little bit, and the rest of them at the end of the concluding portion of the webinar. We're going to move on now to a detailed look at IMU timing features from Reidar Holm. Reidar is a product development manager at Sensonor, a producer and developer of high-precision, lightweight gyros and IMUs. Reidar works MEMS R&D and design, ASIC design, low-stress package design, system design, assembly and calibration, and high-volume production for automotive MEMS pressure sensors, accelerometers, gyros, and IMUs. He has a degree in electrical engineering and electronics from the University of Manchester Institute for Science and Technology. Reidar, please give us your presentation.
Thank you, Alan. Hello, everybody. Thank you for listening in on this webinar and giving me the opportunity to tell you a little bit about Sensonor and to give you some insight into timing features of our tactical grade gyro modules and IMUs. Sensonor is not a provider of complete systems for navigation and stabilization. Our field of expertise lies within designing and producing high-precision gyro modules and IMUs. However, our customers do, and through discussions and feedback from them, we have implemented several features that hopefully are added value when it comes to synchronization and timekeeping. So, who are we? Our history can be illustrated by this tree. Sensonor was founded in 1985. However, our roots go all the way back to 1965. The trunk of the tree symbolizes our solid fundament into design, production, and quality know-how based on the delivery of more than 250 million safety-critical components to automotive applications during close to 2 decades. In 2009, Sensonor changed its focus to tactical-grade gyro modules and IMUs. These are all based on the very same MEMS gyro that was developed and used in the rollover gyro. The branches and fruits of the tree symbolizes the large variety of applications and customers served by our standard portfolio of products, in contrast to the automotive era with limited but highly application-specific products. Sensonor's products cover a wide range of applications within navigation and stabilization. Some of the major application areas are stabilized radars and anti-missile systems, LiDAR mapping systems, and short-term navigation. Here is an overview of Sensonor's current product offerings. From a size, weight, and power point of view, the products are very competitive, having a weight of only 55 grams, a power consumption of roughly 1.5 watts, and the size close to a box of matches. The STIM 200 series are gyro modules. The STIM 300 series are IMUs, all at tactical grade performance. The products with the suffix H denotes that they come in a hermetic package. The STIM 320 is currently being introduced. This product has the best gyro and accelerometer performance and has some additional timing features, which will be described in more detail later. When referring to our products in general, we call them STIMs. Here is a functional block diagram of STIM 320. All sensors are synchronized during startup. Raw data, which has been digitized and low-pass filtered, is delivered to the calibration and compensation module at a 2 kHz data rate. This is the heartbeat of the IMU. Data transmissions to the application is done as data packages or datagrams over an RS-422 interface. Timing for ASICs, ADCs, and microcontroller comes from the same crystal oscillator, having an overall accuracy of 50 ppm, ensuring synchronous sampling of all sensors. There are individual, continuously sampling 24 bits ADCs for each of the sensor signals. Only the temperature signals for compensation are multiplexed before being digitized. In addition to the RS-422 input and output, there are 4 special signals available, dedicated to synchronization and timing issues. The STIMs can be configured to output data continuously or only when receiving a signal on the external trigger input. This timing diagram shows the continuous data transmission mode with 1000 samples per second output data rate, hence transmitting every second sample data. The STIMs can be configured to output data at data rates between 125 and 2000 samples per second. When choosing output data rates below 2000 samples per second, attention should be given to choice of filter bandwidth, or alternatively utilize the implemented features like average or integrated output to avoid issues of folding. Back to the timing diagram. At the top, one can see the 2000 samples per second heartbeat at which a new set of raw data is available. This is an interrupt-fed signal to the microcontroller. If a datagram is to be transmitted, the microcontroller will pull the time of validity line low. This time delay is between the internal time tick and the TOV line is in the order of 1 microsecond. This means that the application can use this signal to synchronize to timing of the IMU and to know when a datagram is being transmitted. The TOV line will go high after the transmission of the datagram is completed. However, this transition is not as sharp and well defined as the transition at the start of the datagram and should not be used for timing purposes. As can be seen from the timing diagram, the transmitted data is based on the raw data from the previous internal time tick. Once the internal time tick has been received and the TOV line pulled down, the microcontroller will start to calibrate and compensate the latest set of raw data, having this available in time for the next time tick. Hence, in continuous data transmission mode, there will be a constant delay of 0.5 millisecond between the availability of raw data and start of transmission of the compensated data. When the stim has been configured to external trigger, the latest available compensated sample is transmitted when a negative transition is received on the external trigger input. In the transmitted datagrams, there is a field containing latency information. This will now contain the delay between the time of the external trigger signal and the time of the internal time tick when the raw data for the data in the transmitted datagram was received, enabling the application to adjust to the IMU data, to the timing of the IMU data. In this case, the TOV will not act as an envelope for the datagram, but still communicate the stim heartbeat by pulsing low at each internal time tick. It is now time for a short break. Over to you, Alan.
Thank you, Reidar. A couple of questions from the audience. First for Reidar, what is the jitter in the TOV signal?
Well, that's a good question. We have measured the jitter in the TOV signal to be roughly plus minus 100 nanoseconds for the STIM 300 and 377H, and 250 nanoseconds for the STIM 318 and 320.
Noted. And going back to the previous presentation, John, you listed a lot of different approaches for timing IMU measurements. Do you have any particular one of these that you prefer or find easy to use in real systems?
Well, if I have a system I'm building that has an NTP or PTP server, then and there are sensors that support that, then that becomes a very easy integration because I can just plug it in and everything is aligned, and that's quite easy to use. Of course, you know, not every system is like that, so then there's other approaches that we mentioned, but I personally love it when I can use NTP or PTP.
And another one for you, John, is a bias in the time tag better or worse than having jitter in the time tag?
Well, that really comes down to if you can measure and account for that bias. If there's a known bias, then it's actually very easy to account for. You can just subtract it out and you're good. If it's unknown, you know, perhaps it can be estimated. But you know, if there is a bias that can be accounted for, then that's not a really big problem. Really, then the jitter, that's the part you don't know. You can't really know what the jitter is, and that sort of introduces a level of noise, in a sense, into your system. So, you know, having very low jitter levels, you know, makes it possible to have very precise measurements.
Exactly. And we heard from Reidar a minute ago about the jitter in the TOV signal from the STIM. Lori, let's ask a question of our audience, and then we'll get back to Reidar's presentation.
Okay, let's do that. Coming up on the screen, our second poll question for today. How important is it for you to understand what is going on in the IMU with respect to timing? So we've got your responses there on the screen. Inner details are critical. Helpful to know inner details, but not required. I like a black box. I just need a number. Or doesn't really matter. So we've got 37% inner details are critical, 43% helpful to know inner details, but not required, 19% I like a black box, I just need a number, and 1% coming in with it doesn't really matter. So any thoughts on these responses?
Well, I'm going to give a few very basic thoughts, and then I'm going to ask the panel to weigh in what they think about this. Obviously, we see that the majority find inner details either critical or useful, and inner details is just what Reidar is talking about. Well over a third, it's critical, so got to have them. and nearly half saying that they are very helpful. John, Reidar, Bjorn, anything to add to that?
Yeah, this is John, having worked with a lot of inertials, often those inner details are not even available. So I actually appreciate sort of seeing, the inner details of Sensonor. And it's sometimes challenging to use systems where you kind of have a lot of questions. So I suspect there may be a lot of people that kind of wish they knew the inner details, but just can't get it.
And this is Reidar. It seems like we have, or that the audience really have understood what this is about and that they have joined the right webinar.
Exactly. You're on the right plane, and we're going to continue flying. Reidar, please continue with the second half of your presentation.
Thank you, Alan. I will now spend some time on quantifying the delays through the signal chains. Starting off with the sensor and ADC group delay. The gyro has a relatively large bandwidth in the order of 2.5 kHz, having close to no contribution to delay or phase in the pass bands up to the largest bandwidth of 262 Hz. The delays are mainly due to the decimation and low-pass filter being cascaded integrator COM filters, or CIC filters for short. One big advantage with these type of filters is that all frequency components pass through the filter with the same time delay. In other words, they exhibit a linear phase behavior. The sensor and ADC group for the gyros is 0.71 milliseconds. The 10G accelerometers have a bandwidth of in the order of 400 to 500 Hz, which gives some contribution to the delay or phase. The main contribution comes from the 24-bit A to D converters. The ADCs in the STIM 318 and 320 are running at a higher speed compared to the STIM 300 and 377H, leading to a lower group delay at the expense of somewhat higher power consumption. The sensor and ADC group delay for the 10G accelerometers in STIM 300 and 377H is 5.9 milliseconds, and for STIM 318 and 320, 1.51 milliseconds. The low-pass filters are third-order CIC filters with selectable bandwidths between 16 and 262 Hz. The lowest group delay is naturally achieved when using the largest bandwidth. To compensate for the difference in sensor and ADC group delay between gyros and accelerometers, an optional group delay can be turned on for the gyros. This effectively delays the gyro raw data a given number of internal time ticks, resulting in a delay of 4.5 milliseconds for STIM 300 and 377H and 1 millisecond for STIM 318 and 320. We then see the 0.5 millisecond delay for calibration and compensation, as previously described, the TOV delay of approximately 1 microsecond, the delay to start of datagram transmission is maximum 80 microseconds and is due to the need of calculating this 32-bit CRC when the decision of data transmission has been taken. And finally, we have the time of the data transmission, which is dependent on the chosen bit rate, the number of bytes in each datagram, and choice of stop bits and parity. Here's the gain and phase response of the raw data, hence the combination of sensor and ADC group delay and the low-pass filter group delay, with the low-pass filter bandwidth set to 262 Hz. The dotted line in the plot for the accelerometers represents the lowest specified bandwidth of 100 Hz. the difference in time delay or phase is not significant with respect to the variation in bandwidth. The phase bandwidth of the gyros at this point is 114 Hz and 84 Hz for the accelerometers. This picture is quite similar when it comes to the use of external trigger, as can be seen here, except for the latency not being constant at 0.5 milliseconds. Here is an example on the calculation of total delay. The low-pass filters have been set to 262 Hz. The datagrams are continuously transmitted and have a length of 28 bytes. The RS422 bitrate is set to 1.8 megabits per second. As can be seen, this gives a total delay of 2.89 milliseconds for the gyros and 3.69 milliseconds for the accelerometers. In terms of phase bandwidth, this results in 87 Hz for the gyros and 68 Hz for the accelerometers. If the gyro delayed option had been enabled, this would add 1 millisecond to the total gyro delay, leading to a delay between the two being very close. STIM320 offers a pulse per second input. This can be configured in two modes: time since detection or PPS filtered. In time since detection mode, the PPS signal will be an interrupt-fed signal to the microcontroller. Once an edge with correct polarity has been detected, the time is recorded. The PPS field of the datagram will contain the elapsed time between this time and the time of the event that triggered a datagram transmission. This either being the internal time tick or an external trigger. The PPS data is 24 bits with a resolution in microseconds. Hence, the time since detection can take values up to over 8.3 seconds. When the PPS input is configured to PPS filtered, the PPS signal is sampled at 32 kHz and fed into a third-order CIC low-pass filter similar to the filters used for the gyro and accelerometer signals. All filters in the STIMs can be configured individually for each sensor axis, and PPS filtered. To obtain the same time delay for all signals, the same filter bandwidth should be used, and the gyro delayed and PPS delayed options should be chosen. In case of the PPS signal, this will for STIM320 result in a delay of 3 internal ticks or 1.5 milliseconds. Finally, the STIM320 offers a counter restart signal. For some applications, using the TOV line for time synchronization represents too much effort on the receiver side due to its relatively high frequency. Therefore, a counter restart signal has been implemented where the application can program a more suitable interval. The STIM320 contains a 16-bit counter which increments each internal time tick, hence each 0.5 milliseconds. Every time the counter starts from 0, a pulse appears on the CRS output. The counter interval can be programmed to intervals between 0.5 milliseconds to just over 32 seconds. In the example shown, the interval has been set to 5 counts or 2.5 milliseconds. When the counter reaches 4, it will restart from 0 and give a pulse on the CRS output similar to the TOV pulse when the STIM is configured to external trigger. To summarize, several features have been implemented in Sensonor's product to support synchronization and timing issues. A TOV output giving the application IMU timing information on when raw data has been sampled and filtered. an external trigger input giving the application IMU timing information relative to its own timing through the latency information in the datagrams. A PPS input giving the application IMU timing information relative to its own or timing of other components in the system. And a CRS output giving a similar functionality as the TOV output, however at a selectable rate. Alternatively, this feature can be used to make the IMU act as the source of timing for the system and thereby saving space and cost and reduce system complexity. The table summarizes the available timing features on the different products. All products support TOV output and external trigger input. The STIM 320 has PPS input and CRS output available. And that completes my presentation. I hope you have enjoyed it. And back to you, Alan.
Thank you, Raja. We'll have the opportunity to ask questions about this presentation at the following the next one at the end of the webinar. We encourage you to input your questions in the question panel on your interface. Next, we're going to look at measurement and analysis involving railway and overhead lines, and this is going to be given by Bjorn Scott, Chief Technology Officer at Latronics AB, Stockholm-based. Latronics turns cameras, lasers, and all sorts of sensors into advanced measuring systems for industry and railway. Bjorn has a master's degree in physics engineering at KTH Royal Institute of Technology, and he coordinated the LiDAR patient positioning project at Karolinska Institutet. He has developed product platforms at Latronics since 2000, from the CRAD Sentinel laser scanner for patient positioning and radiotherapy to the Latronics OTG system, measuring everything railway from track geometry to catenary wire. Bjorn specializes in system design, image processing, geometrical calculations, and hardware-connected programming for optical and inertial measuring systems for railway applications. Bjorn, floor is yours.
Thanks, Alan. So my name is Bjorn Scott, and I've been designing measurement systems for more than 20 years, as Alan says. And I work at this small Stockholm firm called Latronics. Our core skill is in dimension measurements, and we have developed platforms for many different industries. However, I happen to like trains and railway. I always did. I think it's a really comfortable way to get around, and it makes sense to the environment. And it impresses my 8-year-old daughter when I tell her that I've spent the morning attaching stuff under a giant locomotive. It even impresses some of her friends. During the last 15 years, Latronics and I have slowly, sometimes painfully, turned into experts at railway measurements. It does make sense to do the kind of measurements that we do. Avoiding large deviations in the track avoids catastrophic derailments. Keeping the catenary wire position and wear reasonable avoids tearing down the wire. Setting maximum allowed limits to the shape of the railway lets you ride safely and comfortably in the train, and it minimizes the wear of both the track and the vehicles traveling on it. Measuring track quality and catenary wire used to be extremely hard, requiring specialized vehicles and a host of experts. Typically, it has been performed by some national entity capturing every part of the network once or a few times per year. This sort of scheduled measurement are super important to keep the track quality up and to plan future maintenance. We are proud to say that our platforms, the Latronics Owls, forms a measurement backbone in Sweden, Norway, Denmark, and in Turkey. But take a look at the rail-borne excavator in this image. It is switching out old sleepers, carrying the rail for new sleepers. This work involves digging in the stones, pulling out the old sleeper sideways, pushing down the new sleeper, attaching it and filling back some of the stone. This really affects the shape of the track. Yet, 1 hour after I took this picture, a passenger train passed this very spot. Do you think that was safe? Well, yes, it was safe, because the train passed at slow speed for several weeks until one of the few national measurement vehicles passed this spot. All trains had to pass at low speed, causing lots of delays. Can you see the small yellow box on the back of the excavator? That is our new compact self-contained OTG, the Owl's track geometry, at an early test. Before and after each shift, the excavator makes a measurement run to check the track quality according to the EN 13848 norm. This will revolutionize this kind of maintenance work. The team will be able to verify and prove that the track is safe to ride, and they can tell the maximum allowable speed. The electronics OTG turns anything into a measurement vehicle. It is portable. 2 people can lift it into place. If you have a 1960s locomotive, well, weld an attachment and you're good to go. You have a 2-way vehicle? Great, you can hook it up to the tow bar. Well, if you have a brand new railway car, good for us. The OTG is tested well about 200 kilometers an hour, and we can give you more if you need. Let me tell you a little bit about the OTG interface. I'll not go into the details about the output curves, but there is horizontal and vertical alignment, telling how bent the left and right rails are for a specific chord base. The alignment faults are related to your comfort. You can feel the bumps. Also, the larger the bump, the faster it grows, so it is important for planning maintenance. Twist tells how well aligned the left and right rails are to each other, typically at 3 and 6 meter wheel axis distance. If this figure is poor, then one of the 4 wheels risk losing rail contact, leading to a derailment. The system output reports an alert list in different formats, among them this pretty alert view showing what is wrong and exactly where. Oh wow, except we anonymized for this presentation. The operator connects to a dead simple 2 buttons interface that shows a map, the track, some notifications, and a couple graphs rolling by as you go. From the start, the OTG is just a bunch of sensors. The heart is the IMU and the speed sensor pair. These tell the sensor path through space. But we are interested in the track. Contour sensors measure where the track is relative to the sensor, and this gives a track path through space. We could have stopped there, but a GPS tells a position, and this gives you the track ID, the kilometer and the meter. An NTP time server lets us integrate easy with external system. All this feeds into a PC. But a PC is an inexact and inefficient way, typically, to time every input packet. We want sub-millisecond accuracy of all measurements. If the IMU and the contour cameras do not agree on time where they are, we will calculate the wrong path through space. It just does not matter if we have a perfect IMU and perfect contour cameras. When we sum the paths, they must be synchronized. I was asked how the timing affects our output, and I frankly did not know. So today I simulated a typical vertical alignment fault, a bump, at a typical speed on a typical car, and found that 1 millisecond sync error meant 2% error in the output amplitude of the bump, the alignment. Better than that is good. 10 milliseconds meant 20% amplitude error, and 100 milliseconds meant 100% error. It was perfectly misaligned. Stable synchronization is absolutely essential. Without it, we will detect and report an error that is not there. So we want to offload the timing from the PC and lay it onto a dedicated synchronization unit. You see, all sensors except the speed sensor keeps feeding into the PC, but the speed sensor feeds directly into the sync unit. Let's dive into the OTG. There are 40 different types of sensor synchronization going on in the OTG. Starting from the top, there is a STIM 300 or STIM 320 that accept a PPM pulse, a pulse per meter input that we bring to it every 500 meter and adds that to the output. Then there is a GPS that outputs a PPS, a pulse per second signal, every 5 seconds. When the sync unit sees this, it freezes a tachometer value and sends to PC. Then there is a camera, third from the top, that takes a tachometer position in the trigger package and adds it into the output. And in the bottom there is a smart Ethernet sensor using network time protocol. This may be anything from an entire measurement system to a web camera. And we want to have the NTP stamp into the same framework as everything else that we measure so that we can synchronize to this external unit. First, let me show you how a sync unit works. Then I'll tell you why. There's a counter for the speed sensing tachometer pulses, telling the traveled length along the track. On every 25 centimeter traveled, the sync unit triggers the cameras with an Ethernet package containing the counter position. On every 500 meters, the sync unit sends out the sync out pulse, which we call the PPM, for pulse per meter. Also, the sync unit reacts to a PPS input, freezing the counter position value. Twice per second, the sync unit sends its state, the position and the frozen position, to the PC. These are saved to file. This lets the PC remember the exact counter at which the sync in, the PPS, occurred. You see, the sync unit is only interested in position actually, not in time. We will bring that in later. Using this extra feature lets the PC, it doesn't have to react to any real-time events. The camera is triggered and the exact counter of the sync impulse is known. So the PPS and the PPM should be slow pulses. Typically, we try to keep it at 5 seconds because then the PC doesn't have to do anything real time. It can go to sleep for a second. It doesn't matter as long as it keeps up with the data streams. So let's look closer at how the sync unit links time and position. The sync unit sends a trigger to the camera every 25 centimeters. The camera returns a position in centimeter and the exact time for every trigger to PC. The GPS works in the time domain and samples every 0.1 seconds. How do we connect the GPS? The GPS outputs a PPS pulse every 5 seconds. This is sensed and reported by the sync unit. The event is visible in the GPS output data stream. The sync unit captures a counter position on receiving the PPS output from GPS and sends it to PC. The last output from the sync unit is added to each data row from the GPS, in blue to the left. See that when the GPS time reaches even 5 seconds, the last sync pos is updated. For every 5 seconds in the GPS output, we know the exact counter position. Thus, we can interpolate the counter or camera time for any GPS row. Can we capture the PPS pulse out from a STIM unit in the same way? Well, As a matter of fact, yes. In the STIM 320, there is a CRS, the counter restart signal. You can connect that to a second input capture channel to freeze a counter into a third column of the sync table. The GPS, PPS, and the STIM CRS work the same. They are sparse events, visible at an exact event time on an output pin and easily found in the sensor data stream. But if we add more and more sensors, the sync unit must support an input pin for every one of them. This is kind of clumsy. Is there a way to avoid a new channel for each sensor? Could we have a common sync signal for everyone? Well, yes, this is how we chose to do it. The sync unit provides an output pulse every 500 meters. There are inputs on both the STIM 300 and the STIM 320 and very nice functionality. On STIM 300, it is an analog input called AUX. On STIM 320, it's a logical input called PPS in. The inputs are filtered in the same configurable filters as the other signals, providing known delays. Now, let's turn to the IMU and also see how we can incorporate the time from an NTP time server. Again, we have the sync unit and camera giving exact position in centimeters and the exact time for every trigger to PC. The IMU works in the time domain and samples every millisecond. How do we connect the IMU? And can we connect the NTP timer server the same way? Here's a trick. The sync unit outputs a PPM signal every 500 meters. The IMU senses a PPM signal and adds it into the output to PC. The picture in the bottom shows the signal in the output from the STIM 300. It's filtered in the IMU with the same type of 131 Hz filter as the other signals, giving extremely predictable timing. You see that every 500 meters we can connect the IMU to the common position and time. Thus, we can interpolate the common position and time for any IMU measurement. The same thing goes for the NTP server readout. We had to add an extra microprocessor for that, but it's still fairly simple. This is an example measurement showing 10 kilometers of raw data. Both the GPS and IMU have been resampled into kilometer from measurement start using the sparse interpolation system. You can see the sparse 500 meter PPM pulses captured by the GPS in the lower right plot. And you see in the zoom in up to the right how it looks. The takeaway here is that synchronization is necessary to good repeatability. Here are two measurements on the same track overlaid in blue for upwards and red for downwards traveling. On the x-axis is kilometers and meters. It is hard to even tell that there are two curves. The accuracy is well within the EN norms, and the GPS repeatability is so good that we can start the next step, finding trends over time, looking for track that deteriorates. I'm really looking forward to that step. Thank you. Back to you, Alan.
Thanks very much, Bjorn. We have some questions from the audience. First of all, for Reidar, can the 50 ppm timing accuracy be improved?
Yes, certainly. The crystal oscillator that we are using comes in a 20 ppm version that could easily be exchanged and implemented immediately without having any major redesigns.
And can the total delay be reduced?
Yeah, this is a bigger question. The main contribution lies within the sensor and ADC group delay and the low-pass filters. if you remember the page with the example. For the gyro, both these functions are implemented in ASICs, which then will need to be redesigned. For the sensor and group delay, we believe that 0.5 milliseconds out of the 0.71 millisecond easily can be removed. And reducing delays in the low-pass filters actually means increase of bandwidth and thereby also increase in noise. So there is some trade-offs there. But we believe it should be possible to reduce the total delay for the gyros from 2.89 down to closer to 1 millisecond. But as I said, by redesigning the ASICs. For the accelerometers, the ADCs can be speeded up even further, however at the cost of increased power consumption. And again, the low-pass filters can be increased similarly to the gyros. And here we should be able to come from the 3.69 milliseconds down to around 1.5 milliseconds. Yeah, so it's certainly something that would need a redesign, but it is still significant time to reduce if so wanted.
All right. We're going to pause briefly in the question and answer session to show the audience a resources slide for more information on Sensonor IMU Gyro products and Foundry services, and very interesting application of Sensonor technology in space. We had a webinar on that some time back, very active in the small satellite sector, and a technical note on radiation testing of gyro and IMUs. Lori, let's have one final question for our audience, and then we'll turn back to their questions.
Okay, the final question is on the screen. Which of these would be most added value for your application? You can select all that apply on this one. So pulse per second input, counter restart signal output, external trigger input, time of validity output, or IMU clock synchronization by NTP or PTP. All right, so those are our poll results. Any commentary here before we get back to the Q&A?
Well, I'm largely unqualified to comment on what these answers mean, so I'm going to turn to our panel and ask them, gentlemen, any of you, what do you think of the various answers, keeping in mind that obviously many people have selected more than one? What do you think of these answers? What do they indicate about our audience or their applications?
Well, this is Reidar. Also, let's say, being the father of design of our products, I'm very happy to see that so many people in the audience would appreciate, let's say, the new functionality related to the PPS input for that product, and so maybe something we should consider also to implement in some of the other products.
All right, more to come from Sensonor. Stay tuned. Bjorn, a question for you. Where do you see OTG track measurement, your product, 5 years from now? How is it going to develop?
Yeah, but my main goal is to keep simplifying the entire chain of track geometry. I mean, to enable more usage scenarios. I mean, we pretty much have hardware and data acquisition and reporting generators covered, and well, that's a start-stop interface, a two-button interface. And the system pulls a track ID and kilometer and meter from maps, so the operator can keep the focus on driving the car. But I mean, the challenge is to turn our typical customer from being a national government giant, which is nice, of course, but to being a small contractor with a rail-borne excavator. That's where the measurement is most needed, directly after work on the track. So that is my goal, to enable that change.
And another one for you, Bjorn. What did the STIM series mean to the OTG track measurement product?
Well, it kick-started the project when my friend Eric Berggren turned up with a STIM 300 a few years ago. It lets us make a compact and simple measurement unit with more than enough accuracy to handle the EN norms and all that. The STIM 320 now lets us deliver that same accuracy down to lower speeds and for longer wavelengths. And so Sensonor has been important to us, and they are really nice guys. They are a good group of people to ask questions to. You get good answers.
I'm sure that's music to their ears. Well, here's a question for Reidar at Sensonor. Why does latency information in the transmitted data packages contain only a part of the total delay?
Well, the total delay could certainly have been transmitted in the datagrams, as the STIM knows exactly which low-pass filter setting, which bit rate, and RS-422 configuration that is in use. However, as each of the low-pass filters can be set individually, this would mean that delay would need to be transmitted for each sensor axis, making the datagrams significantly longer and requiring thereby much higher transfer speeds to enable this. So we made a decision to keep, let's say, the variable factor in the datagram, and then put all the constant delays in the data sheets, as they can be handled by the application as constants.
I've got a couple of questions for John Raquet. John, any thoughts on the feasibility of having a common master clock distributed to various sensors?
I think that's sort of an approach that definitely can work. And then the question is, how do you distribute that? And it can be done by one PPS approach, like we've talked about, where you have a master clock distributing its time to the others, if the sensors can bring that in. And that's really the idea too with a NTP or PTP system, is you have a master clock that is the NTP or PTP server, in a sense, that then other ones can use.
And in a follow-on to that question, the listener wants to know, my experience is that relative drift in timing is often the problem. For example, the GPS discipline's TDOA estimation process or radars.
Yeah, so when you're talking about relative drift, I think probably what is being thought of there is you have clocks that maybe initially were synchronized, and then you assume, well, I started with synchronized clocks, and so I'm good. But, clocks drift at different rates, so over time, they kind of come apart. And so in most systems, you really need a way that you can continually update that synchronization, either like the previous question, distributing a clock, or having a continual way to estimate that drift and correct for it.
Okay, thanks, John. Bjorn, do you get a problem with the RC train EMC to the GPS? This listener says, we've seen this on the GPS antenna on top of the train.
No, I haven't seen that, but we have a pretty tight integrated box with our electronics inside it and an integrated antenna in the cover. So maybe that is why we don't see it. It's definitely different if you have a long antenna cable going outside the car. But we have did a few installations on electric cars and have not seen an EMC problem. So, well, no, we didn't see the problems, but I'll keep an eye out for it. I mean, sometimes for temporary installations, we have not put this communication box with the GPS antenna up on the roof with all the high voltage, because it wouldn't be safe for a temporary installation. So we put it down in the cabin, just inside a window. So maybe that is why we didn't see it.
Understood. Reidar, does the IMU block have an integrated barometer?
Thank you for that question. As I said, we do listen to our customers, and our products is really a result of that. The main philosophy is to make, let's say, a few standard parts that fits most needs, and so we put in as much flexibility, programmability, and so on as possible. When it comes to barometers and also magnetometers, these have been features that we have been looking into, and certainly are, let's say, technically feasible. The big question is there sufficient need out there for such features? And so far, let's say, the barometer need has not, let's say, been found to be sufficiently, let's say, interesting. But if you have a big need, then don't hesitate to contact sales@sensonor.com, and we can discuss it.
Exactly. The moral of the story is, if you have a need, tell Sensonor, and if you have a question, ask Sensonor, and we'll have contact info coming up shortly to do just that. Well, it's been an illuminating webinar. I'm going to, in a second, ask each panelist in turn to give us a concluding comment, or perhaps to stick in something that they just occurred to them or they didn't get a chance to say earlier. But I want to thank the audience for attending. We had a good representation around the world. And I want to thank Sensonor for sponsoring the webinar, making it possible. And I want to thank each of the gentlemen who spoke here, John Raquette, Reidar Holm, and Bjorn Scott, for taking the time. Considerable preparation goes into these webinars, and I think the results speak for themselves in that regard. Thanks again to the audience for attending, and just going around the panel for a final comment. John?
No, thank you. It's been enjoyable. I'd say that the big thing, I think, is it's really good to think about these things up front, and not once you have a system put together and then try to figure out how to solve these problems after you've already have built it. Thank you.
Reidar?
Yeah. Yes, it's been enjoyable to have this webinar. I hope I've been able to show everybody that there could be some interesting features in our STIBs that could be useful for systems. And I appreciate that so many people listened in to this webinar.
And final, Bjorn.
Yeah, well, thanks. It's been fun adding a bit of reality connection with a specific implementation and the product to this feature. Well, it's thank you.
Yeah, and I want to say how interesting I found it. High-speed rail is is a great interest of mine. I wish we had more of it in this country. Developments in Europe and Japan I follow with great interest, and I think that's an important trend for the future. And obviously, track precision is a vital to keep the trains on the track and running safely. Well, we've done it again. We've conducted a in-depth technical webinar. I hope you all have profited from it. Thanks again. From inside GNSS and inside Unmanned Systems, this is Alan Cameron saying fare thee well and best of luck, best wishes. Lori?
Absolutely. And just to echo, thank you so much for joining us. This is Lori Dearman saying, hope we see you on the next one. Bye for now.